Howdy everyone, this is Liu from Texas A&M University, and I'm here to present the paper SHARP, Fast Incremental Context-Sensitive Pointer Analysis for Java Programs. As we all know, pointer analysis is fundamental and have been researched for decades. It has many dimensions and research directions. However, most of the existing works require to analyze the whole programs, which is precise but expensive and unscalable. Another direction is to reuse the result from previous analysis and only update according to incremental code changes. Among all the incremental works, IPA and D4 are two most recent developed techniques for Java programs. Their incremental algorithms soundly and efficiently update both call graph and pointer assignment graph pack iteratively according to code changes. They handle both statement additions and deletions. Especially for deletions, they leverage local neighbor properties to update lazily only if a pointer is not reachable from an object node. D4 also introduces an incremental static data race detector as the application of IPA, which takes statement change as input and output new races triggered by code changes. Due to its fast performance, D4 allows developers to obtain instant feedback during development phase instead of testing or production phase. So critical races can be fixed before the real deployment. However, both works are built on context-insensitive on-the-fly algorithm, which has poor precision in pointer analysis result, as well as the dependent application result. Here are the numbers of detected data races by the same algorithm in D4, but using different pointer analysis results. As we can see, the context, no matter it's k-cosite sensitive k-CFA, which uses the most recent k-cosite as context, or k-object sensitive, which uses the most recent k-receiver objects as context, they can significantly improve the precision of data race detection. Intuitively, we would think if we could integrate incremental algorithm with context sensitivity. If it's possible, how do we guarantee the soundness as IPA does? How to generalize such new algorithms to different types of contexts? We present SHARP to solve the above challenges. We adapt IPA to both call-side sensitive and object-sensitive algorithms, identify the redundant computation for call statement deletions. Besides, we discuss the different parallel scenarios for GitHub commits. A context here is composed of a sequence of context elements. Here in the example, it's C1, C2 to CK. For Java programs, method call statement determines the context element for k-CFA, while object allocation determines the one for k-object sensitive. No matter which type of context is used in pointer analysis, both new and invoke statements determine a call graph node, which further defines a set of pointer and object nodes. Hence, we need to carefully handle the deletion of new and invoke statements if we want a general, sound, and efficient algorithm. Firstly, I will introduce the redundant computation. If we naively apply IPA to context-sensitive algorithms, for example, k-CFA, where the most recent two call sites assemble the full context of a method call, we will see redundant change propagation to the pointers that later will be identified as invalid. Take the code on the left-hand side as an example. After we delete the call to M2 on line 7, the call age between M1 and M2 should be removed. Now, M2 nodes become invalid, and so do the points to constraints created by its enclosing statements. Then, we delete the constraints and propagate the change in points to set. Note the propagation here involves a chain of nodes. Since the call to M3 on line 10 has no valid callers in call graph, call site S4 also becomes invalid. Now we realize the previous change propagations are redundant. A faster way is to simply empty their points to sets instead of running the check and propagate rules as described by IPA. The same scenario exists in k-object sensitive algorithm when deleting a new statement. To avoid such redundancy, instead of propagating changes immediately, we pre-compute all the invalid context elements right after the deletion of a method call. For this example, we identify S3, S4, and S5 are invalid context elements after deleting line 7. Then we leverage the invalid elements to identify invalid nodes and edges in call graph and peg. Every call graph node, pointer, and an object node which has S3, S4, and S5 in its context becomes invalid and should be removed. Since they have no outgoing edges pointing to an invalid node in the graph, we directly delete them. The rules to identify invalid context element for k-CFA also works for k-object sensitive, where methods are distinguished by their receiver objects. After deleting the object allocation on line 2, we confirm the invalid context element is O0. Similarly, every call graph node, pointer, and object node which has O0 in its context becomes invalid. A difference here is we have an invalid pointer pointing to a still valid pointer, P2 to P3. For such cases, we delete their connecting points to age and run the deletion algorithm, check and propagate, to update the points to set of P3 and its reachable nodes. Except for incremental context-sensitive algorithms, we also discuss different parallel scenarios according to the real-world GitHub repository commits, which works for both context-sensitive and insensitive incremental algorithms. Let's firstly see how the parallel version of IPA works for one-statement change. According to parallel IPA, after deleting statement y equals x and its corresponding age, the change delta, which is O1, is confirmed and removed from points to set of y. Now, 3 change propagations will be run sequentially, labeled by P1, P2, and P3. This propagation by path 1, P1, is to update Z and its reachable nodes. This propagation path P2 is to update for statement y.f equals b. This propagation path P3 is to update for statement m equals y.f. This example shows the worst case that all three changes, delta 1, delta 2, and delta 3, repetitively update a sequence of nodes with the summarized change delta sum. To be specific, Z and its reachable nodes are updated by delta 1, which is O1, and delta 2, which is O2, twice. However, even though they update the same path, we can still run the three propagations in parallel. The three cases here show all the possible propagation scenarios for a change delta I along its propagation path pi, and summarize the change delta sum along the common path p sum. Case 1 and 2 have no repetitive propagation, since they either have no common propagation path or only require one time of propagation for one change. Hence, the propagations for different delta I can be run in parallel without conflict. Case 3 involves repetitive propagation, just like we saw in the previous example. These can be classified to two situations for any delta I and delta j from paths pi and pj. If delta I and delta j have no common object, just like delta 1 and delta 2 in the example, no matter which path propagates its change first, the finalized change in points to set of z is always the same. Otherwise, like P2 and P3 in the example, both paths propagate the same change O4 to M. No matter which path is scheduled to propagate the change delta first, data will be removed from the first points to set on P sum. The later propagation from the other paths will confirm that data has been removed and run check and propagate for the rest change if exists. For the above, we discussed the details for the parallelizations of one statement change in Sharp. We can also parallel the handling of one statement change from different methods in a commit, where we will see similar scenarios as before. For more detailed proofs and discussions about redundancy, efficiency, and conflict, please refer to the paper. We implemented Sharp in the MATLAB framework and performed an empirical evaluation on 4 large real-world Java projects on GitHub with frequent code commits and long code commit histories. The evaluation was on the most recent 10 Git commits with an average number of 1,386 additions and 900 deletions for each commit. To compare the performance of incremental algorithms, we run Sharp with our parallelization on the following context-sensitive pointer analysis algorithms: 1 and 2 CFA, 1 and 2 object-sensitive. Meanwhile, we run IPA with context-insensitive algorithm. We firstly run the initial whole program pointer analysis on the most recent code available in GitHub. The full-time are shown in column 3, and the statistics of generated pegs are in the last 3 columns. Then we utilize the computed points to analysis result to initialize Sharp and apply its incremental algorithms to analyze each commit. On average, Sharp provides fast feedbacks for each commit changes within 19 seconds, which is 180 times faster than rerunning the whole program analysis. Meanwhile, IPA is 193 times faster than rerunning the context-insensitive algorithm. This means Sharp can achieve the similar speedup as IPA does, and is as efficient as IPA. In general, Sharp can achieve faster speedups than IPA sometimes, even though Sharp is running on much larger pegs with millions to billions nodes and agents. For more details, please refer to our paper. Thank you for listening to our talk.
So this is a question from Manas. We have been exploring incremental analysis too, and on the other hand, keep facing the challenges of slower point analysis, and your work looks useful. So thank you. So the question is, do you handle reflection that usually mars static analysis? Okay, so it's been answered already, but Bojen, can you say something?
Yeah, sure.
Yeah.
Thank you, Dr. Igashashi, to hosting this event. And yeah, I would like to say, reflection is the culprit of all static analysis techniques. Yeah. So here we just conservatively handle it by following what Walla have, which is to infer the type of a reflection call and all possible functions of that type, and to analyze all of those functions, which is really conservative. And while Suit has a better reflection resolver, it used the Temiflex, but it actually, I don't think it can work for incremental analysis. You a really faster performance, because it really needs you to run to dynamically generated call traces, so you can see what are the reflections actually. So yeah, that's mainly my answer.
Thanks.
Oh yeah, thank you.
All right. So, any other questions for the first talk, Bojen's talk? You can raise your hand if you want to be on the stage to ask questions. If not, actually, I have one question for you.
Mm-hmm.
So your you have context sensitivity and object sensitivity. Can you combine them?
Yeah, sure. Actually, when you using context, you can hybridly using any type of context. For example, you can use both cosine sensitive and object sensitive. You can also add some sensitive in there, so which is a cheaper version of the object sensitive. So yeah, you can decide what you want to, which one you want to use at where program. It's possible, and that's why we want a generalized algorithm that works for mostly classic context, because we want those hybrid contexts also can use it. But actually, we didn't evaluate this part, but that's a good point, actually. Yeah.
So it's implemented, but not evaluated.
No, yeah,
Oh,
the algorithm works. The algorithm
okay.
works. Yeah, but we only implemented it separately. Yeah.
I see.
Yeah.